Now that you've completed the finite state machine, you can go ahead and work on your truth table and come up with your equations. So how to fill out the truth table. So since we have only 2 states and we have 1 single bit encoding, right? If you had 3 states or 4 states, you would have to move to 2 bits. But since we only have the 1, we have a P0 value and an N0 value. So present state is 1 single bit. Next state is 1 single bit. Your other input to this finite state machine is the transition line variable. So that's the E greater than 6. So on the input side, you have 2 variables. So you can fill out your left-hand side of the truth table the way you normally would. So 0, 0, 1, 1, 0, 1, 0, 1. Then on the next state side, right, or the output side, the next state is 1 output. Then you have each of these variables here. So IS's value, iLoad's value, ZS value, ZLoad value. So you have 5 outputs and 5 equations that you're going to need to come up with. So in state 0, with a 0 for your flag, right, you would stay in state 0. In state 0 with a 1, you transition to the next state. Again, in state 1 with a 0 for your flag, you transition to state 0. And in state 1 with a true value for your flag, you stay in state 1. So that's your N0's value. Now fill in these. These are going to go quickly. These values, remember, are based on present state values. So here's your present state 0, 0, or S. Here's your present state 1, 1, or T. So in S, you have 1s across the board. 1, 1, 1, 1. Right? So go ahead and fill those in. And then in state T, or state 1, you have these values. So 0 for S, 1 for load, 0 for S, 1 for load. Same here. So the equation for the load, if we could do that quickly, right? If I had to write out the equation, I know you can't see because of my hand being in the way, but these are just equal to 1. Okay, and now focus on the others. And these two are identical to one another, I see. In this case, in N0's case, I'm going to write it down here on the bottom. So N0 is equal to, right, this one. So this would be complement of P0 ANDed with the E greater than 6. ORed with P0 and E greater than 6. So by simplification, you could factor out the E flag, and you're left with P0 complement ORed with P0, which becomes a 1. So you're just left with this. I'm running out of space, so I'll just leave it there. Okay, so this becomes a 1. Okay, and then the equations for the other two. So IS, I'm totally running out of space, but let's see. I underscore S is equal to, wherever you have a 1, right? So I see that it would be, the complement of P0 is the same here and here. This is changing, so it is the complement of P0. It's similar logic as to what we did here. And then Z underscore S is the exact same. So complement of P0. And if you plug those into K-maps, that's what you would get also. All right, so those are your equations. What you could do at this point now is draw the circuit. And I'm not going to ask you to do that simply because these are so simple, right? We don't have a lot of inputs and outputs going on, no AND gates, no OR gates, none of that. Okay, so I'm going to stop here.